Today under statistical thermodynamics, we will be looking at the partition functions, and the first partition function is the translational partition function. Now in previous video we have seen that the partition function qt, it represents the translation partition function. It could be written as summation of gt e raised to et by kt, where gt is the translational partition function and et is the translational energy. Now this is similar to the particle in the one dimension box, or if we are looking at three dimensions, so it will be similar to the particle in three-dimensional box. So initially we will be considering one dimension, and then we will be adding all the dimensions. For translation partition function, the statistical weight factor is unity, that is the energy levels or the translational energy levels, they are non-degenerate, and the energy obtained is n square h square upon 8 ml square. So this is the length of the box, and n are the number of particles, h is the Planck's constant, and m is the mass. So this is the expression that we are getting for the energy when we are considering the movement of the particle in one dimensional box also. So we could obtain the energy from there. Initially we are considering that particle is moving only along one direction, and the total translation partition function will be translation partition function along x-axis into translation partition function along y-axis into translation partition function along z-axis. And when we multiply all the three quantities, when we substitute the energy, and we will be converting this summation into integration and further solving it, we will get the partition function along any single direction, and then we will be multiplying all of them, and hence we will obtaining the partition function along all the three directions, and hence the translation partition function will be 2 pi mkt raised to 3 by 2 v upon h cube, where again m is the mass, k is Boltzmann constant, t is the temperature, v is the volume, and h is the Planck's constant. Take this numerator into denominator, and we could write capital lambda is equal to h upon 2 pi mkt raised to 1 by 2, and hence we will have qt is equal to v upon capital lambda cube, and this lambda, it is known as thermal de Broglie wavelength. Now for an ideal gas, we know that v is the volume, so pv is equal to nRT, and hence if we have ideal gas, then in place of volume we could substitute nRT by P also. So in place of volume, if volume is not given, this could be substitute, and m is the mass of single molecule. It is the mass of single molecule or single atom that is considering, and capital M is the molar mass. So generally whenever we are considering molar mass, so molar mass divided by Avogadro's number will give us the mass of single atom, so that needs to be substituted, and hence this is the partition for this is the translational partition function. So when you substitute and solve it, we will get the amount of the translational states that are accessible to any particular system that is under consideration. One more very important thing, that if we are considering that all the things are constant, then we could see that translation partition function is directly proportional to the volume. So translation partition function is the only partition function that is dependent on volume. It is also dependent on temperature and mass as well, as we have seen in the earlier lectures, but it is also dependent on the volume, and this is the only partition function that is dependent on the volume. Hope the concept is clear. Thank you very much.